our goal for today is to solve rational equations. Keep in mind our definition from rational equations from a little while back. Quite simply, you're looking at equations, things that have letters in them, variables in them, that are written as fractions. So you're going to solve for x when it and some of its friends are embedded in an equation that has fractions in it. That's our goal. And just to start off with, you got a little bit of vocabulary to go ahead and copy down. One of these words we have already defined. That would be the term extraneous solution. And then cross-multiplying, that particular definition is a definition you probably took care of quite a bit in geometry when you did your proportionality theorems for similar figures. But in definition number 1 there, you're asked to define cross-multiplying, and that is a method. It's just a way to solve a rational equation when each side of the equation is a single rational expression. You have also seen this term as cross products. You might remember, solving with a cross product when you solve proportions. You could use that idea that the product of the means is equal to the product of the extremes. We'll do a little bit of that today. And then number 2, the term extraneous solution. That's just an extra solution, an extra answer. So it's an apparent solution that must be rejected because it does not satisfy the original equation. So those are your words there. To be clear, I'm going to go ahead and just take a second to flip through our slideshow today. And you're going to get 2 methods from me in this final section of Chapter 8. 2 methods. The first method is cross-multiplying. And we reserve that particular method for when you see a proportion in your problem. For instance, that guy there, that's a proportion. You have basically a fraction set equal to a fraction. So we're going to take care of problems like this today in class. And you're going to see it again for some independent practice problems. And then in example number 2, I'm actually going to show you another way that you could write that as a proportion and then solve using cross products. But ultimately, the second method is utilized when you don't have a proportion. Do you see what makes this not a proportion here in example 3? Well, yeah, there's like an extra term on the right side of this equation. We don't have a fraction set equal to a fraction. So we can't just jump right on into like cross multiplying to solve this particular example. So you'll see that it's from example 3 on that we do tomorrow. So today we're just going to focus on how can you use cross products to solve for x in a rational function. But tomorrow when you get to class, you're going to get your second method. We reserve it again for when you see like crazy looking fraction problems. When you can't necessarily just jump right into using cross products, we use something called the LCD method. So we have an LCD method in this last section of Chapter 8 as well. So we're going to use the LCD method a little bit more tomorrow. All right, so back at the beginning. In example 1 right here, I'm asked to solve the rational equation by cross multiplying. So you'll see here how I know I'm supposed to cross multiply is that I have one single fraction, a numerator over a denominator, set equal to precisely one other numerator and one other denominator. So right now I'm going to go ahead and put an X right over my equal sign. And that just shows me the direction, gives me a little insight into how I can set up my cross products. For instance, 20 times the quantity of x minus 2, that product there, is actually the same as 5 times the quantity of 2x minus 5. A couple different ways you could solve for x from this point forward. Anybody want to give me one idea as to what you would do next? So now this is a simple linear equation from earlier in the year, we think. What do you want to do next? What do you think, Danielle? What do you want to do next? Distribute's what you want to do? Cool. You could also just divide both sides by 5. It's an option. Both are valid. So Danielle would take 20x minus 40 and set that equal to 10x minus 25. Great. So we could distribute, and then we really can't solve an equation when there's variables on both sides. So Matt, what do you think you would do next? I agree. So subtract 10x, we move all of our variables to one side and then our constants to the other. So now on this side we have 10x minus 40 equals negative 25. And then according to Matt, we would then add 40 to both sides. 40 and negative 25 combines to make 15. And then 10 times x equals 15. By my division property of equality, I can divide both sides by 10 to get x by itself. X ends up being, you could say, you know, that's 3 over 2. You could say, you know, as long as you're not rounding, you could use a decimal. You could say that that's 1.5. But for right now, those are my answers for x, 3 over 2 and 1.5. It's going to be super important in this last part of Chapter 8 that you check for extraneous solutions. There's only been a couple cases throughout the course where we have to check for extraneous solutions. As we come up on the final exam, I am going to take a moment to review those with you so that you know on your multiple choice final, is there an extraneous solution hanging out as one of your options? You know, and how do you check for that? We're going to review that actually in a couple minutes. But for right now, I just want to practice checking for an extraneous solution. Remember the rules. You have to check it in the original equation. So not in the first step, but in the actual original pipe-written rational expression. You have to take your answer for x and substitute it back in. So what we're going to go ahead and do right now is copy down our original equation, and I'm going to leave a blank where I see my x. So my original equation was 20 over 2 times x, 2 times blank minus 5. And I want to see if that is equal to 5 over blank minus 2. So in that blank right now, I'm going to go ahead and maybe plug in 3 over 2. Because I like the fractions better when I don't have a calculator handy. And I'm going to go ahead and simplify each of these fractions a little bit. So for instance, I have 20 over 3 minus 5. And I'm trying to see if that is currently equal to 5 over negative 1/2. So this is going to be 20 over negative 2 on the left side. And I'm trying to see if that's going to be equal to 5 times, multiply by the reciprocal of the divisor, negative 2. Hey, how about it? Negative 10 is totally equal to negative 10. So that answer worked. X equals 3 over 2, or 1.5, is actually the correct solution. So you can go back now and circle that up as your final answer. Questions about that? Real quick, oh my gosh, some of you are already on the independent practice and finishing it up. Wow, good job. Okay, real quick though, before we get too far into the independent practice, I just wanted to review with you under what circumstances you have to check for extraneous solutions. So you can make a little list in your notes if you would like, or you could, you know, we'll talk about this more, like I said, before you go ahead and take your final exam, but I just wanted to, you know, start the conversation now. The earlier I start it, usually the better it goes come final exam time. We now got our last case, just now, our last case of where you have to check for extraneous solutions. Very last one. So you know that if you have to solve a rational equation, you now have to check that particular response to see if it's extraneous. Does anybody remember another case or two where you had to check for extraneous solutions? Calvin, do you? Absolutely. Very good, Calvin. Anytime you have an absolute value equation, it's real common that you get two answers. One of them could be extraneous or both. So you always want to take a minute whenever you solve an absolute value equation. Nice job, Calvin. You do have to check for extraneous solutions. What's another case? We just did them. The end of chapter 7. Daniela. Yes, very good. When you solve a logarithmic equation, very good, Daniela, you have to check for extraneous solutions. Do you remember what forces out the extraneous solution in logs? By chance? No. Can you take the log of a negative number? No, so that's what happens. You're going to end up taking the log of a negative number and it doesn't work out for you. So yeah, you always have to check logarithmic equations too, to make sure you don't end up taking a log of a negative number for your response for x. Okay, that's great. Any more? Can you take the square root of a negative number? So, very good, you can't take the square root of a negative number, which means you have to check for extraneous solutions in what type of equation? Well, not quadratics, because honestly, if you have like x squared plus 3x plus 7, you have to solve that for x. Let's say that's equal to 0. You're going to get two answers. They could be real or imaginary, but whatever you got for x, you didn't have to then take that x value and plug it back in and check it. So you can actually get imaginary solutions for those. Very good. Specifically, if it's an even root, yeah, you got to look for that. Very good. That's also kind of tied into another. All right, well, we got a good list going. We'll work with that. We'll come back to it. But yeah, looks pretty good. Questions about when to check for extraneous solutions? All right, so with that, I see some of you have already moved into your independent practice problems. I just want to make sure, because I have people coming into this room from different geometry classes, different geometry backgrounds. I just want to make sure you could solve a basic proportion. So you're going to go ahead and take a minute right now. For number 1 and number 2, I want you to solve those for x and make sure you check your solutions to make sure they're not extraneous. So I'll go ahead and give you a second to do that. Okay, so Maddie, what'd you get for that first one there? Perfect, very good. And Marissa, what'd you get for number 2 there? Very good. Questions about those two? They may not get those answers, not know what they did wrong. They both do work, by the way, when you went to go check them. Questions about that? All right. To be honest with you, the ones on your homework assignment aren't necessarily this easy. So I wanted to kind of give you some tougher proportions to sort of look at and to sort of bridge the gap between today and tomorrow and give you a little bit of a tougher proportion to solve. I wanted to just briefly talk about example 2. You might notice as you just look at example 2, we are asked to solve this rational equation and it says it's going to have one solution. So we are going to have to check to see if there is an extraneous solution for this particular problem. And it gives you a hint. It says multiply each side by the LCD. That's the method we're kind of going to talk a little bit more about tomorrow. And we're going to start tomorrow with example 3. We might actually even start it today. We'll see how it goes. But as far as example 2 is concerned, they give you a little bit of a hint, but we're going to ignore the hint for a minute, and we're going to try a different method. Okay, I have a question for you first before I jump on into working out how to solve for x in this problem. Can you just put an x over that equal sign and use cross products to solve? Marissa definitely said no. Why did you say no, Marissa? You're totally right. Why can't you put an x over that equal sign? Go ahead, Heather. Yeah. So you have multiple denominators over here on the left side. Like if you go to set up an equal sign or a cross product right over your equal sign rather, like what happens to the 8 over x? What are you even going to do? So this isn't a proportion yet. But what we could do is actually do the addition that's on the left side, because you're so good at this. You just handed in section 8.5, or you're about to hand in section 8.5. We can go ahead and just focus for a second on simplifying this left side of the equal sign here. Add those two fractions together and make it a single fraction. And then use a proportion or cross products to solve. So that's what I'm actually going to go ahead and do. So before I teach you the LCD method tomorrow, I wanted to show you this. In step 1 of this particular method, step 1, you would simplify, or maybe we call it combine, any fractions that are already in the problem. Sometimes they're on the left side, sometimes they're on the right side, but you want to combine any fractions that you see in the problem. And we did say just a few moments ago that we're going to try to simplify this left side right here. I'm going to find the sum of 8 over x plus 11 over 3. Now my question is, I can't add these right now because the denominators aren't the same. So thinking back to the last section we just finished up as a class, I need the LCD for x and 3. What's the LCD? Good, Ryan? Yeah, very good. So if we operate under the assumption that the LCD is 3x, that first denominator is missing the factor of 3. What did I do to the bottom? I have to do to the top. And then Ryan said our LCD is 3x, so this guy's missing the x on the bottom. And what I do to the bottom, I have to do to the top. So if I simplify this, I get 8 times 3, which is 24, plus 11x, all over 3x. So now I can take this fraction and replace it, or substitute it in, where 8 over x plus 11 over 3 was, because we found that sum to be 24 plus 11x over 3x. So in step 2 of this particular method, we set up our proportion, or our rational equation, and use cross products. So we set up our proportion and we cross multiply. So I bring down the 24 plus 11x over 3x from the previous part of the problem, because as we just said, this here and this here are the same. I can use those interchangeably. So I bring down the condensed version, and now I'm setting that equal to negative 14 over x. And now we have, as promised, a little bit of a tougher proportion to solve. We still use cross products though, so I am going to go ahead and make an x over my equal sign, and I'm going to write my cross products. So essentially what I have right now is, rewriting this as a product of the means set equal to the product of the extremes. I have x times 24 plus 11x set equal to negative 14 times 3x. And now I'm going to give you a few moments now to distribute, expand, get one side equal to 0, factor and solve that particular equation for x. So I'm going to go ahead and let you work through that just a bit. Just to show you kind of where you're headed with this one. As I walk around, it looked really good. What you're going to get, initially when you distribute and you set one side equal to 0, you end up getting an equation that looks like 11x squared plus 66x equals 0. So as I walk around, that looks good. Remember that the first method you always try when it comes time to factor is the Gcf method. So I saw most of you trying to take out the 11x. You get one side equal to 0, you factored, and now when you solve, you use the zero product property to solve. So you'll see I had to set 11x equal to 0, and then I had to take x plus 6 and set it equal to 0. Notice in the left side there, 11x equals 0 made x equal 0. 11 times what number gives you 0? That number has to be 0. But then I put an x through it. Anybody tell me why I had to do that? If you know, well. Yeah, you can't divide by 0. So poof, extraneous solution came out of your response there. Do you see that? If you look at the original equation, and it says it right there too, no division by 0, you're going to get your extraneous solutions in this chapter mainly because your x value is going to somehow make the denominator equal to 0, and you can't have that. So as Daniela was telling us earlier, like, hey, you know, in logarithms, when we solve for x, we have to check for extraneous solutions, and those logarithms can't be logs of negative numbers. Well, here, you're going to be able to really quickly check for your extraneous solutions because they're going to force out your denominator to be 0. And we can't divide by 0. That's impossible. So again, it's an answer that creates this impossible situation, and it doesn't work, therefore it's extraneous. So that's a little bit of background onto some of the type of proportions you might see on your book assignment for tonight. Okay, are there any questions about this last example? It looked pretty good as I walked around. I was pleased. Okay, so tomorrow I'm going to show you the last method for solving for x in a rational equation. It does involve, you know, taking the LCD and distributing it to everything in the problem. Okay, to wrap up our lesson for today, I need to check or collect rather 8.5 practice B, but I didn't know if anybody had